As you might expect, working with a changing force is going to be slightly more complicated because we have to worry about the force that changes. So its orientation with respect to the displacement could change. So your angle could change, the value of the force, the magnitude of the force could change. All of those things can change. And so what that means is if we have something where we're pulling on it, so initially we maybe have a force that pulls like this, F1, and it works over this distance, which we're going to call little differential distance, dr. And then later on, like the force gets big. So this is the force at later time working like this. And then we keep going, and maybe the force gets really tiny. And so what we need to do is say the work is equal to force F1 dot the little displacement in the first little section plus F2 times however far it goes with that force over this region plus F3 dotted into whatever the displacement is over this region. And these two are a little easier. This one we've got some kind of angle we have to deal with, but basically we're adding up all of these. So if we sum all of these up, it would be the sum over all of these, but as a differential, instead of a summation sign, we do this elongated S for sum, or it's an integral of F dot our dr. Okay, so this is in general a messy expression from where we go from initial to final. But we're going to not do the most general case like this. We're going to make it a little easier. So we're going to look in just one dimension. So now our cosine, this angle between them is either going to be 0 or 1. So we're going to do in one dimension. And we're going to say our work is equal to this integral of f dx. So I don't have the dot product I need to worry about anymore because they're both in the same direction. And the minus sign will just fall out if we need it. And we go from initial to final. So, okay, you say to me, hey, I'm taking calculus 1. We haven't gotten to this crazy symbol. This is an antiderivative. You've gotten to a derivative. So this is the opposite of a derivative. And as we saw in some earlier videos, I said what you need to know about it is that the integral is the area under the curve. So one way to look at this is to say if we plot our force versus our x, our displacement, then whatever this curve looks like, then the work is the area under that curve. So we're going to do this with a specific case of a force that I know something about that I hope will make some sense to you. So if we do this with a spring, I hope you remember, but you may not because we haven't used it yet, is that the spring force changes. It's minus kx. This k is our spring constant. And of course, it has units of newtons divided by meters. Or if you like, a newton is a kilogram meters per second squared all over a meter. So it's also kilograms per second squared. It's good to know the units of everything as we go along. So that's our spring constant. And that tells us how strong a spring is, whether it's a really stretchy rubber band or a really tight rubber band, right? And so if we look at a spring like this that's stretched out, then we know if this is the place where it would be happy, this is equilibrium, where it's unstretched, then when the further we get away, so this is our x distance, the further we get away, the stronger the force is, the spring force. And of course, the spring force is going to be that direction. There's our x. This is our spring force, pulls us back in, okay? So this is our x equals 0, this equilibrium point. So if we take that and we just plot that our spring force, at least in one dimension, this is equal to minus k times x, well, that's linear. That's a linear plot. And so if we look at that, we start out at 0, 0. And then it's got the slope is the spring constant of this, and it's negative, and it's going through 0. So it's going to look something like this. This is a plot of f, where f is on the y-axis and x is like that. So that's my plot. And if we want to know the work, if we go from x equals 0, let's say, x equals initial, let's call that equals 0, to some final point, let's say this is the final point, then we know if we start at x equals 0 to some positive final point, like I've got drawn here, call it 4 if you want, or 2, it doesn't really matter, then we can find that by finding this area, okay? And so that area is pretty easy. It's the area of a triangle, so the work is the area under the curve. That's what this integral is. So an integral we calculate is the area under a curve. And so in this case, this is an easy one to do. That's why I picked it, because it's an easy one to do, the area. And so the area is the area of a triangle, which is 1/2 base times the height. 1/2 the base is just this x final distance that I have, and the height is just my force final, okay? And so if I put my force final, which would be minus kx final in, then the area or the work is minus 1/2 kx final times x final, or x final squared. That would be the work to stretch it from equilibrium. So the work done by the spring, in this case is the area under the curve, would be minus 1/2 kx final squared, okay? To go from equilibrium to x final. From equilibrium at x equals 0 to x final. Okay, great. Let's see if a negative work makes any sense, though. So let's look at what's going on. If we look at this, our spring force, notice that our displacement is in that direction, right? That's the direction of the displacement, but our spring force is like this. And so the angle between these two, the angle between them, if we go ahead and set them up, so there's force S, that is this phi, this angle phi is 180 degrees, and cosine of 180 degrees is equal to -1. So getting a negative value makes sense. What does it mean for something to do negative work? It means the displacement is going against the direction of the force. If you think about it, this spring force didn't really help us get to some position out here. It doesn't willingly want to do that. When the spring has a positive work is when you release this spring, and so this block starts to slide back towards equilibrium, then the spring force is in this direction, the displacement is also in that direction, and so all of a sudden you get positive work. And so that would be on this same graph going from this point back to this direction, so going back the other way. Okay, the area still looks like it's negative, but we really do care about the direction that we do this integral. Okay, now for those of you who know something of calculus, I want to give you how you find this from calculus point of view and get a slightly more general expression. Okay, so the mathematical approach to this, this is a mathematical approach to do it graphically, and it's a fairly straightforward way to do this graphically, but you will eventually have the tools for this, and so I want to point out that you can get your work is equal to minus, from initial to final, putting in your force of minus kx dx. K is a constant, just like in derivatives, you can pull that constant out. I'm going to go ahead and pull this minus sign out also. Have work equals minus k, the integral from initial to final, so this is a definite integral, x dx. And just like with derivatives, because this is an antiderivative, we have a power rule. And for those of you who've gotten there or who have already taken calculus, you should be able to do these power rules. This is just, you just use the rule minus k. This is now x, anything to a power. I'll just point out integral x to the n dx is equal to x to the n plus 1 over n plus 1. That's sort of our power rule right there. So this is x to the first power. So x to the 1 plus 2 is 2 over 2. And then we evaluated at the limits from the initial to the final, which is maybe something you don't remember or you may not have gotten to. So this work is equal to, now I have a minus 1/2, bringing that 1 over 2 over, times a k. And then the way you do these limits is you plug this one in and then you subtract that one. So you've got x final squared minus x initial squared. And this is the more general expression. It tells you the work done by a spring, and it works no matter where you start. If you start at the at x equals 0, great. If you start somewhere in between, right, then you're finding the area of sort of this trapezoid right in here, okay? And so this will work, and you can just use this expression if you want. Of course, if x initial equals 0, we're back to the same expression that we had before. So the varying force, the one varying force we're going to have for a while is going to be the spring. We will eventually put some other forces in, but that's going to be somewhere down the line, okay? So this is the important one to know how to do to find it from a graph. You may also need to be able to read off graphs and find your work done by finding the area under the curve. But I won't ask you to do this kind of integral until we get close to the end of the semester when everybody has gotten there in their calculus.